This is a conversation with Peter Woit. He's a theoretical physicist and a senior lecturer of mathematics at Columbia University. He's one of the most popular critics of string theory and the author of the acclaimed book and blog, Not Even Wrong. In this conversation, we discuss his journey falling in love with physics and maths. We talk about theories of everything, Twistor Theory, string theory, the nature of symmetry, and we talk about some of the biggest problems in academia today. This is No Time. If you like what you see, then do hit subscribe on YouTube, follow on Spotify, or rate 5 stars in Apple Podcasts. This project continues to take a lot of my time, money, and efforts. If you'd like to see it continue, do consider making a donation on Patreon, Anchor, or Instagram. If not through monetary contributions, then do consider sharing these episodes, leaving your likes and comments. All forms of engagement, they really go a long way. For the forms of love and support, you can follow this channel on Instagram or Twitter, or follow me personally. And now, it's no time. I would like to start off with 2 quotes. The first is by Albert Einstein. The name might ring a bell. Who once said that pure mathematics is, in its way, the poetry of logical ideas. The second quote is by Bertrand Russell, who said that the pure mathematician, like the musician, is the free creator of his world of ordered beauty. Around 50 years ago, you were poring over books of astronomy in a local public library when you pulled on this book on astrophysics, and you discovered that you really need to understand mathematics to understand the equations that calculate the structure of stars. Let's go back to that time. Let's go back to the 1970s when you first discovered mathematics. What was that feeling like? What drew you into maths in the first place? And like Einstein and Russell, were you immediately able to spot the poetry in mathematics, the creativity, the music, and the beauty of maths?
Well, it's actually a little bit different. I should make it clear that I actually first got really more seduced by the physics. So I was learning the mathematics as I went along, and I always loved mathematics. But the thing that really first seduced me was kind of learning about astrophysics and about astronomy, and then about the seeing that there are these equations which describe the interiors of stars, and that by solving this equation, you could understand what was going on inside a star, which I thought was amazing. So I wanted to kind of know where do these equations come from. So part of it was the the amazing fact that mathematics could describe the world, but also the as I learned more and more, it became clear that there were these kind of amazing, deep ideas about physics that were behind this, and I again started to learn more physics and really became very much seduced by the whole story of quantum theory and quantum mechanics, especially. It's which has this truly amazing history, and and the whole history. It's a history about physics and about philosophy, about people trying to understand the world in a very different way, and it's also a story about mathematics. That there's also it also really required new mathematics. So that was kind of the initial progression. Later, when I went to college, I actually I was majoring in physics, but I took a lot of mathematics courses. I took some very challenging mathematics courses, and even took some graduate courses in math when I was undergraduate. So that was, but the beginnings were more in physics, and to me the interest in mathematics was always very much wrapped up with the physics, with the fact that this this really beautiful abstract mathematics was not what was showing up also at a very deep level in the physics, and so there's this deep connection between the real world and deep mathematics.
Was there a point where your love for mathematics started to surpass your love for physics, or you completely deviated away from that path?
Well, not really. I think it's always, to me, what's always been most fascinating is the way the two are linked.
Right.
And so I started out my career in physics. I got an undergraduate degree in physics and a PhD in physics, and had my first postdoc were in physics. But throughout all that time, I was very interested in the mathematics behind the physics, what was going on. And my PhD research project was, it was about physics, but it involved some very challenging mathematics. It involved a lot of topology and geometry, and so from early on, that's true. And then when I got a postdoc, I went to Stony Brook, I was at the Institute for Theoretical Physics there, but it was it's actually in the same building as the math department. It's not in the building of the physics department. It's kind of the top floor of the mathematics department building. And so I actually spent I ended up actually spending, I think, more of my time talking to the mathematicians there than to the physicists, because I was more interested. I was learning more from them than from. I wasn't so interested in what the physicists were doing, and so that was kind of the beginning. And then from there, there's a long story about my career, but I ended up. One reason for ending up in mathematics departments was that I could actually get a reasonable job in a math department, which was not so easy in physics. But if the job situation were different, maybe I would have stayed in a physics department.
Yeah, we will definitely talk about the job situation. But I have a follow-up question for you here. Edward Frankel, professor of mathematics at University of California, Berkeley, he had once said in an interview that mathematicians are insulated from society because it is such a pure subject. It draws in very specific psychological types. For me, mathematics was a refuge from the cruelty of life. In your book, Not Even Wrong, you talk about the divergent path that maths and physics had to take in the 20th century, where you have described instances where many physicists who were struggling with the problem, they could have easily solved the problem if they just reached out to the mathematicians in the same institution, or even shared the problem with the mathematician that they're having lunch with on a daily basis. What is your take on the current state of maths today? Do you think people in academia still feel that mathematicians are working on really abstract ideas that have no connection to the real world, that are not tangible at all? Or do you think it's trying to come together again after that fork it took in the 20th century? Or maybe I'll go as far as saying they have to come together if you have to solve any of the problems.
I think it's one reason I wanted to write a lot about it in that book was that I think it's actually a very complicated story, and there's really to me if you look at it, it's a complicated and really fascinating story, especially the story of the relationship between mathematics and quantum mechanics, of figuring out what how to understand quantum mechanics and mathematics, and it's a complicated story of in some ways things diverging, but also things coming together, and continual discovery of these fascinating deep points of contact between the subjects. And so I think probably the last great period of that was actually in the 80s and 90s, and especially through the work of Edward Witten and other people. There were some especially Witten together with the mathematician Michael Atiyah. There were some really, they just made these amazing breakthroughs in understanding of new ideas at a very deep level of how quantum field theory and geometry and mathematics were related. And that, since then, I think that subject, has become less active. But now I think it's a very interesting situation that when I was hired at Columbia by the math department, I think one reason I was hired was that there was a lot of interest among mathematicians in what was coming out of physics and what Witten was doing, and they saw me as someone who, we should have someone around who understands that and do that. More recently, I think there isn't any kind of central, really active thing like that that's revolutionizing the subject, but it's kind of dispersed. And if you look at what my colleagues are doing in the math department, they're almost all of them, if you look anywhere from people working on geometry to people working on probability theory to people working on even number theory, there's some connection in their work to ideas from physics. So it's become much more dispersed. I mean, I think it would be great if there'd be another, huge advance in some new kind of deep understanding, which, like there was in the 90s. But right now, it's become an interesting situation that there isn't a single point of contact that everybody is very aware of, but there's small points of contact kind of going on everywhere. So it's.
Do you have an intuition about where that central theme or the central equation or problem will come from in maths?
I don't know. I mean, I have my own speculations. I mean, one thing that I'm very fascinated by, increasingly fascinated by in recent years, is kind of very recent work in number theory. Yeah, and that there have been some really the truly great advances that I've been seeing in mathematics in the last few years have been in number theory.
Very quickly, sorry, what is number theory?
Just the the study of the patterns in numbers, about patterns of prime numbers, or their famous problems like Fermat's last theorem. Can do these very simple equations have solutions?
Does Riemann's hypothesis also fall under
Riemann's hypothesis? Something. But there's been a very important kind of unifying idea about what's going on in number theory called the Langlands program.
Right.
And that's been going on since the 60s. But just recently, the past few years, there have been some breakthroughs in understanding about the relationship between geometry and number theory. There have been some new ideas about how geometry and number theory work together. And some of these ideas about geometry that are occurring in number theory, that they are very much the same or similar ideas to exactly some of the things that were going on when I said in this great period of breakthrough in the 90s about the relationships between geometry, topology, and physics. Yeah. So that whole story has started to anyway, there's some recent breakthroughs in number theory that may actually make connection with that story. So, if I had to guess, where some great breakthrough in understanding would come from of the sort that I'm interested in, it would be more in that further work on these connections between number theory and geometry, and to actually see structures there which connect up to some of the very fundamental structures in our understanding of physics.
You have made your prediction for maths. Let's talk about one central problem that's plaguing physics for the last 30, 40, or even more than that years, which is the problem of the search for this elusive theory of everything. So let's introduce this topic. What are grand unified theories? And then what is a theory of everything? What is the problem we're trying to solve? What are we trying to unify?
Okay, so what happened? So when I, so I went to college. I went to Harvard College in 1975, and that was a period, and started studying in the physics department there. That was a period that was just 2 years after kind of this huge set of breakthroughs, which culminated in 1973 in something which is now called the Standard Model. So there's this kind of beautiful mathematical structure called the Standard Model. It was developed throughout the 60s and kind of came together in 1973, and it just does an amazing job. It does too good a job of kind of explaining everything about what particles do. So everything that we see when we study particle interactions, and no matter how high in energy you collide them at a collider or whatever experiment you do to any accuracy, this theory describes it perfectly. And it, and so it was, a lot of the people who had been responsible for developing it were at Harvard, and it was this huge kind of era of triumph there. All this new data was pouring in, which agreed perfectly with the theory. And so, some of the great people who'd been like Glashow and Weinberg, and who'd been working on this for the last decade, they were being kind of completely vindicated, and it was an amazing time. And then, but there was actually kind of an ambitious idea around the same time. It literally, a year or two after the Standard Model first came in 1973, around the same time, there was also beginnings of attempts to kind of further unify, to take the Standard Model has a few different pieces in it, and the idea was to try to find some kind of way to fit those pieces together into something which would be, in principle, explain a bit more and predict a bit more than the Standard Model. Mm-hmm. And that was what these so-called grand unified theories. And actually, it was people at Harvard who were the main people doing this, Howard Georgi and Shelley Glashow. And that, so these are called grand unified theories, and it's really an attempt to do better than the Standard Model, and to have more unification, to unify like the strong and the weak interactions together. And so that's grand unified theories. The other big open question then remains is what to do about gravity. So besides the Standard Model, you have a very good theory of gravity, how gravity works, due to Einstein from early in the 20th century, and that theory has some intriguing relations to the Standard Model. It uses some of the same geometry, but it if you try and treat it the same way as the standard model, and you try and quantize it the same way, that you get into technical problems, and so that's was kind of the other big open problem is what about what about getting a consistent quantum theory of gravity, and then the hope was that you could maybe solve both of these problems. You could get a grain unified theory and also one that included an explanation of gravity. And that's the sort of thing that people would often call kind of a theory of everything. Because at that point, you brought together all of the known kind of fundamental theories we have in physics. But so it's it was I think somewhat of a joke to call it that. But that's anyway, that's what people typically mean by that.
Yeah, so many jokes in physics have just stuck. Like Big Bang the name was meant to be a joke, and now that's stuck as well. Why is there a need to unify theory of general relativity and quantum mechanics? These two tenets in physics that work really well independently, but why is there this need to bring them together?
Well, I mean, to my mind, the best argument is one of aesthetics. That you've got these, why. You got these things that look kind of the same, but they're somewhat different. That you really should actually properly understand what the real relation between them is. And but the other good argument is one of kind of consistency. You can kind of, unfortunately, they're not the sorts of things you can go out and experimentally test, because the energy regimes are too far from what we can create. But you can, in principle, create physical systems where you would need both. Quantum theory and gravity are operating, non-trivially together, and then the current theory doesn't really have a good answer to what's going to happen if in those regimes. So there is kind of consistency and having a theory that really, gives you an answer, and all the times it's supposed to, really require kind of a better understanding of how to fit them together than what we have now.
Is it possible that maybe there isn't a theory of everything? They are meant to be two separate structures.
It's possible.
Okay.
But I would just say that everything that we see, these things, that they're not two completely different things. They're two things with a lot of really intriguing relations between them, a lot of the same mathematics. And one thing that's fascinated me, that I've been very interested in recent years especially, is thinking about reformulating. There are a lot of different ways of mathematically writing down this gravity theory in different ways, and there are certain ones of them which look very much like the same structures in the standard model, and those these are not new ideas. People have been looking at these for years, but I've certainly been kind of very fascinated by exactly how some of the exactly how there really are very good ways of thinking about gravity, which are not that well known, which are very, very, very close to what goes on in the standard model.
Quantum gravity is one of the problems that physics is trying to solve. We're trying to find this theory of everything that might bring them together. Let's talk about one theory that you put forward that might be a step in the right direction, which is Twistor theory. But first, let's assume that I'm a 5-year-old, not hard to imagine at all. Let's assume, it's a big day in my 5-year-old life. I'm learning about a theory of everything, as all 5-year-olds do. How do you explain Twistor theory to a 5-year-old like me?
Okay, so I think I have to back up before. So back up and first talk about spinors, and I should say, and before I do that, I just make it also clear that so Twistor theory is an idea that's really mostly due to just Roger Penrose in the 1960s, and there's been a huge amount of work by various people on Twistor theory since the 1960s, and people have found out all sorts of interesting things about it. So what I've been thinking about recently has been, if you like, a twist on Twistor theory. But really to explain it, to back up, I think it's important to really think about first try to understand what spinors are. So twistors, in some sense, are something that goes beyond the idea of spinors, but spinors are very, very fundamental and very, very kind of not physically intuitive things, but with a really beautiful mathematical structure. But so one thing to say about spinors is that they're really fundamental to our physical theory, in the sense that what people found, way back when they were studying quantum mechanics, was that they were figuring out quantum mechanics by looking at atomic spectra, And they basically found out that every kind of energy state of an atom, which seemed to involve these electrons moving around in the field of a nucleus, that all of these energy states actually were doubled. That if you looked closely, you saw that there were actually two energy states where there should be one. And you could see one way to see this was by putting the atom in a magnetic field, and then the energy levels would split a little bit.
Okay.
But there was this twofold doubling of everything. So quantum mechanics was confusing enough, but all of this, if you ask what's the state of an electron, you had to all this confusing thing about its momentum, where its position, its momentum, Heisenberg's uncertainties, etc.
Yeah.
But you had this other weird thing. It had kind of two states, not just one. And so and then anyway, so there was an understanding that you had to think about this new kind of degree of freedom, and it was called a spinor degree of freedom, because it actually behaves. It does something very non-trivial when you rotate a system. If you take a system and rotate it around, this thing, these two states kind of move around. These two states move around in between each other. So there was something about this twofold extra degree of freedom, which was also involved with geometry and with how the system behaved under rotations. Mm-hmm. So this is, as always, to me, has been one of the kind of great mysteries and one of the fundamental clues about physics, that are all of the matter particles we know about have this property. And so if you want to think about a fundamental theory and you want to think about it in terms of geometry, you really should be thinking in terms of the geometry of these spinors. So that's the physical motivation. Mathematically, then if you start looking at the mathematics of it, we're kind of used to thinking about geometry in terms of vectors.
Yeah.
And so you have, but what you find if you think about vectors in 3 and especially in 4 dimensions, if you try and put space and time together, mm-hmm. so you have kind of 4-dimensional space-time vectors, that you can think of the relation between vectors and spinors in a sense that that spinors are square roots of vectors. The spinors are objects you can put two of them together and in a sense to create a vector.
Okay.
And the mathematics of this, one way of stating the mathematics isn't so difficult. It's everything is a bit not so physically intuitive, because to do this you really need to work with complex numbers. Mm-hmm. But one thing you can do with to study vectors in 4 dimensions is to allow them to be complex, to have complex coefficients, and then think of them as not as a list of 4 numbers like you normally do, but think of them as a matrix of a 2x2 matrix, okay. 2 rows and 2 columns, and so it has 4 entries, and then you can think of the breakup into the spinors is the breakup into the rows and columns. Yeah. A matrix, in some sense, is a product of rows and its columns, and that's very precisely the relationship between, in 4-dimensional geometry, between complex vectors and spinors. The vectors are exactly 2x2 complex matrices. The spinors are exactly the kind of rows and columns.
The rows and columns are also real and complex numbers?
Well, everything is complex. So okay. This is what I've been struggling a lot with in recent years, which I think is very, so the really strange thing about the theory of spinors, one of the strange things is that the theory is actually fairly simple. What I told you is pretty much, that's kind of all there is to say about it, as long as you just deal with complex numbers. Mm-hmm. But your problem then is that, so your space and time have 4 complex dimensions, and that's not right. You should have 4 real dimensions with one of them, time, behaving in some way different than the spatial ones.
Yeah.
So you need something in mathematicians called a real structure. You need some underlying thing that if you throw the complex numbers in, you'll get this these 2x2 complex matrices. And it turns out mathematically that they're different you can create different four real dimensional things, very different real four-dimensional things, which when you throw in complex numbers, you get these matrices. And so that's the mathematics, where the mathematics gets tricky and gets very interesting, and where I think there's actually some things to say which people haven't so much appreciated before. But that's Spinors. And Twistors, in some sense, are okay. So technically, well, maybe it's not a good idea to start with that. But maybe here's one way to say it is that so what the Spinors are telling you, what they're telling about the real world, is if you want to describe the state of an electron, you have to describe it. It's described by a spinor. So if you just look at a point, that state is described by these two complex numbers. So recall these spinors all have to be complex. So there's this kind of two-dimensional complex space of the spin degree of freedom at every point. Okay? So one way of saying what Twistor theory says is that Twistor theory says that really the way you should think about geometry is that you should think of it as a four complex dimensional space, and with these two, if you want to know what a point is a two complex dimensional subspace. So it's if you like thinking more in terms of real geometry, it's kind of a two-dimensional plane inside a four-dimensional space, except everything is complex. So in Twistor theory, the two-dimensional plane is a point. If you want to know what is a point in space and time, well, it's a two-dimensional plane in this four-dimensional Twistor space.
Gotcha.
And so one of the beautiful things that this does is that it makes, in our normal understanding of geometry, these spinors are very mysterious objects. Why are you taking square roots of vectors, and what's going on here? And from the point of view of Twistor theory, it's completely tautological. If you want to know, if you ask the question, what is this spinor degree of freedom space at a point, Twistor theory tells you it is the point. The point is that two-dimensional complex plane. So these kind of answers to why is spinors and where do spinors come from becomes just tautological. But Twistor theory is a very, very different way of thinking about space and time, because points are these complex two-dimensional planes, and so the geometry is very different, and it's anyway, maybe that's enough development of that for now.
Just so I summarize that correctly, instead of imagining points in space-time, now you're imagining those points as planes within a much higher four-dimensional space.
Yeah.
And once you reimagine those points as those planes, it's entirely new structures that you can now start working with and create some fantastic branch of mathematics that you can work with.
Well, once you do this, all sorts of nice things happen. Then there's various symmetries of the situation become much clearer. Anyway, you can use all sorts of methods. Everything is now a complex number, so you can use methods from complex analysis, which are very powerful to study things, and just all sorts of kind of beautiful stuff happens. But this stuff was kind of, it was Penrose who first realized this, and then lots of people in the 70s and 80s worked out a lot of the details of this.
Only mathematicians can get really excited about working with complex numbers. The rest of us would prefer staying in the real world. Okay, so that's Twistor theory. Why is that a step towards the theory of everything, or maybe finding some form of quantum gravity?
Well, so Penrose, when he developed it, was very Penrose wasn't, he came out of a tradition of studying general relativity. So he came up with these ideas by studying general relativity. And so, and this Einstein's theory of general relativity is a geometrical theory. And so rethinking Einstein's theory in terms of twistors gives you, kind of a new way of thinking about Einstein's theory. And there are new things you can do. And this is what, one thing that Penrose and his collaborators were really fascinated by. But But what they found was that while there were some really interesting things you could say about general relativity and gravity and geometry this way, it didn't really kind of quite work. And one way of saying the problem that the basic problem is that Twistor theory is what physicists sometimes call a chiral theory. That it behaves differently if you mirror reflect things. If you do a mirror reflection, you get something different.
That's chirality.
So that's chirality, yeah. Mm-hmm. And so sometimes we talk about it in terms of things being right and left-handed. That your right hand. If you look at your right hand in a mirror, it looks like a left hand. And so there's kind of two. They're two different things.
Yeah.
So the Twistor theory is very much a chiral theory. That the theory of spinors, the way you normally do it, you say that you have two kinds of spinors. And these two kinds, because of the way they behave under rotations, are sometimes called right and left-handed spinors, or positive chirality and negative chirality spinors. And what Twistor theory is telling you is that a point is a spinor, but it's telling you a point is a right-handed spinor, or you have to make a convention, right or left-handed. Sure. But a point is one-handedness of spinor. It is not, and the other handedness of spinors are something different. And so as a theory of geometry, it's very much a chiral theory. It really treats right and left differently. And the problem with general relativity, at least in its normal formulation, is that general relativity is not a chiral theory. General relativity is parity symmetric theory. So what Penrose and the people working with them, I ended up finding out, was that you could do beautiful stuff with the Twistor theory, but it only gave you it only gave you part of general relativity. It just gave you part of it, and because it just gave you, in some sense, the right-handed part, not the left-handed part. Or if you wanted the left-handed part, you had to. And you had to get it separately, but the two are different things. And Penrose actually, I think, called this the googly problem. The googly problem, yeah. So
cricket.
From cricket. So it's something. But I think one thing that I think Penrose realized and had fascinated people in the subject a long time was that while gravity is a parity symmetric theory, it's non-chiral. The standard model is a chiral theory. So especially the part that describes weak interactions. The weak interactions, the left-handed spinors and the right-handed spinors behave quite completely differently. They experience different forces and they behave differently. So so there's always in the back of people's minds an idea. Can we use this to could we somehow use Twistor theory to explain, this stuff about the weak interactions, about the thing that actually is chiral. So, but there never really was I think a really plausible idea about that, because the problem was that Twistor theory was really kind of a theory of space-time geometry, and our understanding of weak interactions is that the weak interactions are something that don't have to do with space-time geometry. They're kind of so-called internal degrees of freedom, which don't have anything. You do rotations or translations, nothing happens to them. So the ideas that I've been playing with in recent years are a way of putting these things together. Anyway, at least conjecturally. I mean, I should say, make it very clear. I'm very far from having an understood and completely written down theory, which I can sell. But I do. I've been playing with some different ways of thinking about Twistor and spinor geometry, in which and I've been recently kind of using the slogan of saying that space-time is right-handed, and saying that, yes, that you really can completely describe all the space-time degrees of freedom in terms of the right-handed spinors, and then the other parity of things, the left-handed spinors, don't actually, which in the standard way of talking about Twistor theory and gravity, you have to use both to talk about space and time. I think there's a way to just use the right-handed ones to talk about space and time, and then to use the left-handed ones to talk about the weak interactions. and to try to bring the things together. But this requires kind of rethinking kind of the whole subject at its basics, and that's kind of the project I'm in the middle of. And so to me, this all looks very promising. I'm very excited about this, but I should say I haven't had that much luck in getting other people equally excited so far. We'll see.
Well, that changes after this episode.
Oh yeah. Well, this was everybody. Yeah.
Everyone's watching. So that's very interesting. So what you're trying to say is these two states, so space-time is right-handed, and you're trying to create a theory for the electroweak force being left-handed. And if you're able to bring them together, then that would be effectively a way towards unifying them, right?
Yeah.
Okay. I want to touch upon an argument that was presented to Sir Roger Penrose that I would like to now present to you. I believe Twistor theory works in 4 dimensions, right? And doesn't work beyond it.
Right.
Right. So the argument that was presented to Roger Penrose was, you seem to be wedding yourself to the reality that we see, which is 4-dimensional. So 3 dimension in space, 1 dimension in time. Whereas other physicists out there are leaving the options open, and they are assigning a Bayesian prior to a hyperdimensional reality, so more than 4 dimensions space. Do you think that's fair criticism, fair argument that you're not leaving the road, you're not leaving this gate open to multiple dimensions, and you're wedding yourself to the idea there are only 4 dimensions in reality?
Well, I mean, that's true, but I think that's actually a strength of this, not a criticism. I mean, the problem with most other ideas about unification, about theories of everything or unification, is that they work in any dimension, and they often work by putting together lots of extra stuff from extra dimensions. Twistor theory is really rigidly about 4-dimensional geometry, but we live. Look around you. There's 3 space and 1 time dimension. So
yeah.
So Twistor theory kind of, string theorists like to say that string theory predicts this, but so if you want, you can say, well, Twistor theory predicts we live in 4 dimensions. So you already have a verified experimental prediction of Twistor theory, which is in some sense very non-trivial.
Is it possible that Twistor theory as well might be like a projection or a compactification of an even bigger theory that applies to multiple dimensions?
Maybe, and people have tried to use it in that way. But the great thing about Twistor theory is its very rigidity. The fact that it really is, there's not, there's this basic beautiful structure, and, you can throw more stuff in, but the minute you do that, it gets a lot more complicated and ugly. If you want the really beautiful structure, it really is a 4-dimensional structure. And so, but that's kind of its virtue. So I don't, I don't, the problem with pretty much any attempt to kind of, to use extra dimensions in fundamental theories, extra space-time dimensions, has been, none of these things in some sense have gone anywhere, that there are just too many possibilities. The minute you start allowing yourself to throw in extra dimensions, there's infinite numbers of possibilities, and you can kind of get anything you want out of it, and you kind of lose any kind of predictivity or any kind of rigidity of the structure, which anyway, so I actually see this as a virtue. That
you brought up beauty. Let's go there.
Okay.
I would like to assign beauty with simplicity as well, because most of the complicated equations end up looking quite ugly to me. So I'm going to read a popular saying in science, which is, this was about mathematics, but I guess it applies to science in general. The essence of mathematics is not to make simple things complicated, but to make complicated things simple.
Yeah.
You just spoke about beauty, about elegance, about simplicity. Do you think most of the fundamental laws in nature, most of the truth in nature is backed by really simple ideas that are so elegant and so beautiful that the moment you see them, it might be right? Or do you think there's merit to the argument that now we have extinguished the extent of simplicity? And this is something John Hogan hinted at the end of Science as well, where now we've reached the ceiling of simplicity, and anything beyond this point gets really complicated, especially in physics and maths.
Yeah. Well, anyway, I just don't see it that way, because I think everybody, that is a popular idea, and I definitely disagree with John Horgan and with a lot of about this in particular. Because what happens, all the people who are saying this, then if you look at they're saying, oh, well, the simplicity is over. We have to do these more complicated things. None of the more complicated things they've done have worked.
Yeah.
So it's kind of like, yeah. So, if people were saying this and then they did some more complicated thing and they went out and did an experiment and, the experiment showed that, well, things worked exactly like this complicated thing. Okay. I'd have to say, okay, well, I guess that's what's happening. But, they decide to make things more complicated, and they make a more complicated version of the standard model, and they announce that this is the way the world has to work. And then you turn on your new accelerator in Geneva, and you find out that it just doesn't work that way. So all of these things have really fallen on their face. So, I mean, my feeling has always been that, our situation is that, we have these really beautiful theories of standard model and general relativity with a great deal of simplicity, a great deal of geometry, a lot going on. But and the reason we're struggling is that we're I would actually believe we're fairly close to having a unified theory, a theory of everything, if you like, and that we're struggling because we're not there yet. We still are missing a couple, one or more kind of deep ideas about how all these things fit together, and so we're kind of looking at this beautiful but not quite right structure that still leaves questions open, and that still has things that you look at and go, wait, how does that? Why that doesn't seem to quite work right? And but to me, all of this is evidence is that there is some. We're just in the situation that we've always been. That the reason we haven't found something better, a better theory, is not that there is no better theory, but that it's just we haven't found a better theory yet. And if you were someday, if you think about it long enough and get the right clues and work on it, this will actually work out. But
okay, so Occam's razor does apply that most likely the most simple and the most beautiful idea is the one that's most likely to be right rather than the more complicated ones.
Yeah, it's partly it's Occam's razor, partly it's just kind of an experimental fact. It's a fact about the world that when you start looking at these very fundamental theories and not try to find a theory that's describing some complicated situation, but you're trying to find a theory that's going to work in the most basic and simple and fundamental questions, these turn out to have this beautiful, simple mathematical structure, and often a very unexpected one. Often the simplicity is something that, it's only after you see this new way of thinking and some new mathematical ideas that you understand this from a point of view where it looks simple.
While we're on the topic of beauty and simplicity, personally, I assign to beauty symmetry as well. So I have to ask you a question about symmetry. In his book, The Tao of Physics, Fritjof Capra says the following words about symmetry, where he says, "The discovery of symmetric patterns in the particle world has led many physicists to believe that these patterns reflect the fundamental laws of nature. During the past 15 years, a great deal of effort has been devoted to the search for an ultimate fundamental symmetry that would incorporate all known particles and thus explain the structure of matter. This aim reflects a philosophical attitude which has been inherited from the ancient Greeks and cultivated throughout many centuries. Symmetry, together with geometry, played an important role in Greek science, philosophy, and art, where it was identified with beauty, harmony, and perfection. The attitude of Eastern philosophy with regard to symmetry is in striking contrast to that of the ancient Greeks. Mystical traditions in the Far East frequently use symmetric patterns as symbols or meditation devices, but the concept of symmetry does not seem to play any major role in their philosophy. Like geometry, it is thought to be a construct of the mind." So what is your take on symmetry? So many schools of thought, so many ideas, so many ancient traditions, so many current ideas as well, whether it's symmetry transformations, symmetry groups, symmetry breaking, supersymmetry, all of them are centered around this mysterious, beautiful concept of symmetry. Do you agree with the Greeks? And maybe this is something Herman Weyl as well alluded in this book, Symmetry, that symmetry represents something fundamental in nature? Or are you more in the camp with Eastern philosophers where you think it's just a construct of the mind, not necessarily fundamental?
I'm afraid I'm in this way. I'm very much a pure Westerner. I don't. I'm with the Greeks on this one. So yeah, and the story of Capra's and his book, I think, is kind of interesting. That he, as I was saying, so this standard model came together with these new ideas came together in around 1973. And Capra, was trained as a physicist and developed a lot of his ideas about the world, which he wrote about in his book, just a few years before, in 70, 71, or whatever. So he, at the time, before 73, and people figured this out, the most common attitude among physicists was that, well, all our attempts to kind of, to come up with to explain things in terms of new geometry and new symmetries have all been failing. It hasn't been working out. And that if we go and look at what happens with strongly interacting particles, they're doing all these complicated things. And, there are a couple symmetries, but the basic, it just gets more and more complicated. You start hiding these things at each other and they just do more and more complex stuff. And there's no obvious symmetries to it. And so, so the attitude, the most common attitude among theorists, at least just before 1973, was that, these beautiful symmetric theories were not, couldn't possibly capture what we were seeing. And so, ideas like what Capra's talking about is, well, maybe you need some very different way of thinking about this in a fundamental way, which doesn't involve symmetry. And so that was the background in which he was kind of brought up and educated, in which he started writing his book. But the problem for him is, I think, by 73, things in 73 started to completely turn around, because people had used these symmetry principles to finish the standard model and to find this incredibly powerful theory. And all of these kind of complex phenomena that had been seen in accelerator experiments all of a sudden now had an explanation in terms of symmetries and in terms of this theory. So he, by the time he was writing his book, it was already, the situation of physics had already started to turn against him. And I think, yeah, so that book, I think when it finally came out, it was already a little bit, it had already been kind of disconfirmed by what had happened in 1973, even though it took people a while, to find the true experimental evidence for it and to really believe it. And I'm somewhat suspicious that we're in somewhat of a current situation, because if you look at what's going on in physics now, there's also a lot of the things that people are working on are, well, I mean, the technicality is a little bit different, but they're somewhat, they're actually closer to what people were doing, in Capra's time in around 1970. People were developing some ideas about very different ways to formulate physics, which didn't involve the same kind of deep symmetries at the shortest possible distances. And so they were doing something called S-matrix theory. And if you look at the S-matrix theory ideas of the late 60s, they're actually much that what people are a lot of people are doing now in theoretical physics is quite close to that philosophy. And my suspicion is that we're in a similar situation, that a few years from now we'll kind of realize that just as those ideas weren't really the right thing to do in the late 60s, that they're not the right thing to be doing now, that there is some new symmetry principle or some new idea about geometry which is going to come in and tell you something new, which is going to explain these things that you're trying to explain in this much more complicated way.
Okay, so you're firmly in the camp of Western philosophers. You think symmetry is fundamental. Do you think if you are in that camp, then you're also assigning a Bayesian prior to the design argument and the existence of a creator?
I don't really have any. I don't really see any kind of relation to that. So this is where, I mean,
well, symmetry could be intelligent design.
It could be, or yeah. I mean, where we are in this physical world, and we have this amazing and complicated relationship to it, and what the and anyway, what the underlying meaning of this existence in this world is I don't have any. I don't think anything. Nothing that I know about physics or math really, I don't think actually tells you anything about that. I mean, it tells you about what this thing is, but whether our kind of relationship of our consciousness to it and our and larger issues about where did this come from and is it part of something else? It doesn't. It's kind of silent on that.
I feel like it's like the sword that's hanging over you when you study Twistors. As you start to unveil these beautiful structures, do you never wonder, like, has this been designed? Like, how is it the way it is?
Yeah. I don't know. I mean, there's another way philosophically of thinking about it. It's just that it's, it's kind of the only way possible for these things to work. I mean, it's kind of, maybe that's in some sense, one of the big mysteries is that, there is this very deep relationship between these theories of reality and these mathematical structures. But mathematical structures, as we normally think about them, are much more general. There are all sorts of possibilities, and you could, in principle, have all sorts of fundamental theories. But there's something very special. There's kind of in some sense there's one mathematical structure which is kind of primary or which is distinguished in some sense, and that's the one that governs the world. And why is that? Why that one? And if we understand mathematics better, maybe there will become some clarity as to, okay, if you really understand what mathematics is, what's the right way of thinking about the mathematics at the deepest possible level, it become clear, oh well, there's something very, very special and about one particular mathematical structure, and then that describes the real world. It's a very pretty picture, but how you want to relate that to any kind of normal human concerns is I'm not sure.
Okay, fantastic. I think that was a fantastic explanation of Twistor theory. As a 5-year-old, I've been following. I've not lost you so far, so that's amazing. I also came across this theory called string theory. You have definitively said that string theory is not a step in the right direction. But before we go there, just to quickly introduce the topic, what is string theory? Why did it originate? What problem was it trying to solve?
Yeah, so actually the origins of the theory is exactly in this the situation I was talking about of the late 60s, that you had these strongly interacting particles doing very complicated things, the standard kind of symmetries and the standard kind of ideas about quantum field theory didn't seem to work. So people were developing different ways of trying to describe this. And one thing that they developed was string theory, which one way of thinking about it is that you, if in some sense our most fundamental theories now really kind of involve kind of point-like particles at a fundamental level, that those are the elementary constituents, that in string theory, instead of having point-like particles, you have your elementary objects are kind of loops. They're kind of one-dimensional closed loops, or maybe they've got ends. So that theory kind of just got going, around 1970, and there were a bunch of people working on it. It was a very active subject at the time. And then 1973 came along, and with the Standard Model. And then once people started to realize how powerful the Standard Model was and how this really agreed with this explained everything that people have been trying to explain now with string theory. By the time I was got to college and graduate school, people had pretty much lost interest in string theory. It really, it was clear that the problems it was trying to solve were better solved by these so-called gauge theories or by the Standard Model.
Yeah.
But it's not so some people, not everybody lost interest, and there were other people pursuing these things, and also again, by the time I was leaving graduate school in 1984, people for quite a while had been thinking about these problems of grand unification and theories of everything and quantum gravity, and what some of them had decided was that you could actually, while string theory hadn't worked out the way you had hoped for the strong interactions, you you possibly could use it to create a theory of everything. And so, and in 1984, there was kind of a technical development that one possible technical obstruction to writing out a certain kind of theory it was shown to vanish in some particular examples, and so that got a lot of some people very interested in trying to go back and pick up string theory and then use it to try to get a theory of everything. And the most prominent of these was one of this kind of great geniuses of our field, Edward Witten, who was really truly amazing. Anyway, and just an amazing person with amazing talent and amazing energy, and he had already been finding out all sorts of new things about the standard model and about that kind of geometry, and he turned his attention to string theory, and he kind of announced in the fall of '84, just around the same time I went to Stony Brook for my postdoc, that this is a really promising theory of everything, strings, and he was really very, people were out of other good ideas about what to work on these problems, and he was incredibly influential. So a lot of people took this very seriously, and I also know most of my friends who were postdocs, they all had kind of the same story. They all at some point would come to me and said, "Oh, I went down to Princeton to talk to Witten about what I'm working on," and Witten listened carefully and nodded his head and said, "Oh, well, that's all very interesting, but you really should be working on string theory because this is really this is where everything is going." And so, he had a huge influence in terms of turning the field to string theory and string theory. I was kind of somewhat of a skeptic from the beginning, because the problem with it was kind of exactly this problem with extra dimensions that we were talking about, that this argument that string theory made sense in some certain situations. Part of the idea was that the strings had to be moving in 10 dimensions. So you couldn't develop a consistent theory of strings moving in 3 space and 1 time dimensions. You could, it seems, develop a consistent theory of strings moving around in 9 space and 1 time dimensions. So you had these 10 dimensions. You had 10 dimensions, and one argument is, well, great, we've got a kind of like Twistor Theory. Okay, we've predicted the number of dimensions. The only problem is they're predicting 10 dimensions, and so you had to kind of explain, well, what about the other 6 dimensions? Where did they go? And so that's where the theory all of a sudden became very complicated, because the idea was that, well, we'll make the 6 dimensions are very, very small, so we can't see them. So 4 dimensions are going to be big, and you're going to be able to see them. 6 of them are going to be really, truly microscopic, and so small we can't actually see what's going on. And we can write down the mathematics and models of what these 6 dimensions do, and then depending on what the 6 dimensions do, you're gonna the strings are going to you're going to see different particles, and the hope is that by finding the right choice of some very, very small 6-dimensional space, we're going to reproduce the standard model, and at least at low enough energies to get something that looks like the standard model. That was the hope. And the people, Witten and other people who worked in this, were very excited about this for at least for a few years. But to me, it was like this really, you were kind of telling me that an incredibly successful theory, you should really throw the whole thing out and start again with a theory which, the minute you tried to make it look like the real world, you had to do some very complicated things with. And I was kind of a skeptic about that, and I think properly. I think the bottom line now, many decades later, is that initial hopes that there were only a very small number of things you could do to make the 6 dimensions work that were consistent. Now it looks like there's just a huge number of possibilities of what you could do with 6 dimensions, and you can pretty much get anything you want out of it. So you can make a theory of everything, but it doesn't predict anything, because depending on it says that everything you see is going to depend on what the 6 dimensions do and what they look like, and they could do almost anything. It really doesn't work. It really is a failed theory, and it's I think the reason I wrote this book almost 20 years ago, and to this day, I'm just kind of shocked that how hard it is to get people to admit that this really just doesn't work, and this is just not viable, and for quite clear reasons.
Just to expand on that, Wolfgang Pauli used to say some theories are wrong and some theories are not even wrong. You have said string theory is not even wrong. What do you mean by that? Why is string theory not even wrong?
Well, I mean, one thing I should say, well, let me say this later. First, so not even wrong is, yeah, so it was kind of Pauli's phrase that, so he was known to, he was heard. Actually, there's very interesting, I've really gone back into the history trying to figure out, did he really say this? And when did he say this? And what was it about? And it's a really interesting story. I mean, all the evidence is, yes, he really did say this, but people are not clear exactly when he said this or about what, or about who, or about what. Yeah. But he was known for, like, he was kind of really pretty irascible and kind of a bit difficult to deal with. And so he was known for, in a seminar, like shouting at people that, no, that's wrong, that's just wrong. But then the story was that he was asked about some particular thing, or maybe one story says somebody was asking about it. Another story was it was in a seminar, but he was in some context evidently just shook his head and said, "Oh, that one's not even wrong." and you can take this as being kind of really obnoxiously, "Oh, well, that's so bad it's not even at the level of being wrong," or a bit more charitably, you can say that there are lots of ideas that as theorists we work with. When you start thinking about an idea, a good example of my is that the ideas I'm playing with Twistors. I mean, these are also not even wrong at this point. There's no way they aren't fully developed enough to say, this is exactly what they are going to tell you, and either this is right or wrong. So not even wrong can just mean, in another context, it's just a still undeveloped idea, which so it's at the point where you just can't tell whether it's wrong or not. So that's the more charitable one. And I should say that over the years, my thinking about string theory has evolved. And when I wrote the book, I was being more charitable, saying, well, this is not even wrong. It's not fully developed. But I think the lesson of the last 20 years is seeing what's happened is that this just doesn't work. And now it's just wrong. I mean, it's just not. I think actually not even wrong may not even be the right word for is really not the word for string anymore. It's just a wrong, failed idea. And that's all there is to it.
You have presented a case for why string theory is not even wrong, or it's just wrong now. Unfortunately, I have no string theorists here today to defend the case. So I'm going to take up that responsibility.
Go for it.
I'm going to play devil's advocate. I'm going to stand up for string theory in their absence. I'm going to list down some popular defenses of string theory against criticisms like yours. I would love to hear your thoughts on them. So let's start. Jim Gates, theoretical physicist at Brown University, he once said that string theory is broken out into the consciousness of the general public before we are finished. Many benefits of exploring string theory are not spoken about. It has allowed us to think deeply about subsequent ideas like calculating the force between electrons, holography, weak-strong duality. All of these are spawned from string theory. I'm going to add to that something Matthew Kleban said, professor of physics at New York University, who was on this show last month. He said that along the way of studying string theory, you learn about condensed matter systems, classical theories of gravity, superconductivity. I'll also add to that what Brian Greene said, your colleague at Columbia University, who said that string theory is a rich source of material that has kept people deeply engaged in moving the frontier forward. Do you think there's value in this argument that even if the primary thread of string theory, pun not intended, even if the primary thread of string theory is facing this dead end, or it's not falsifiable, it's not productive, just continue to work with this framework is creating so many positive externalities and these powerful ideas like the ones they've listed? Well,
yeah, I think the funny thing is all of those statements are actually perfectly consistent with my claim that as a theory of everything, it is just wrong. And I mean, they're not saying it isn't. And actually, Gates, I think, is an interesting thing because I've talked to him a bit and I know his work. And he actually is somebody also who very early on was interested in string theory, but who I think also very early on understood exactly this problem that if you try to do string theory in 10 dimensions, the problem of the other 6 dimensions is just going to make it impossible because you'll be able to get either you won't be able to find any thing to do consistent with the 6 dimensions, or you'll be able to get anything. So he was always in his career has been very interested in string theory, but in trying to resolve these technical problems of how do you get strings to actually work in 4 dimensions. So he's gone in his own route and been interested in things, but I think he early on, I think would actually agree with me that what the theory, everything that Witten was trying to sell everybody, it was not going to work. It was just wrong. So that's an example. But all of them, I mean, they're all saying, well, okay, this didn't work out as it was supposed to, but because of it, we've done all these different things, and there's a very, very long list. Gates has his list, Brian has his list, Matthew Klebin has his list of all these things, and they're all, I mean, it's not that none of these things have any value, but to be honest, and the people who work on them are often very enthusiastic about them, that this is a great idea, and it kind of evolved. So what's going on a lot is you see people now saying, well, string theory is great and string theory is wonderful because, of such and such a subject, which actually isn't string theory, doesn't have anything to do with string theory, but we ended up working on it because of trying to solve problems in string theory. And, okay, but the problem with all of these things is that, maybe not to name any names, but one of the big problems with string theory was just the huge amount of hype that their claims were made for it publicly, which really just were not true, which were unsustainable, which really were way excessive. And a lot of it was just due to the enthusiasm of the people involved. I mean, the story I told you about Witten, I think, is a good example. I mean, he's a genius. He's brilliant. He was very enthusiastic about these ideas. So, people would come to them and he would tell them, drop what you're doing and work on string theory. It's the greatest thing in the world. But he was wrong. People are very enthusiastic about the things they work on. You have to be enthusiastic about the things you work on to keep doing it. But, a lot of, anyway, if you look into what the actual details of what these different people are telling you about, they're a combination of things which don't have all that much connection to string theory, and also ideas which a lot of ideas which have been overhyped in some of the same ways and by some of the same people as string theory was.
If I was a string theorist here today, wouldn't I challenge you with the same question that the work that you're doing with Twistors is similarly, like you said, not even wrong, it's not falsifiable at this stage? So why would I not extend the same argument and say there's no point in pursuing this even further, even if you might discover something else along the way?
Well, it's I think what I'm doing is different, just in the sense that it's very, as I said, unfortunately, I haven't really gotten anybody else very interested in it. So, and I'm not the most brilliant person around. I'm not the most energetic person around. So I've been thinking about this, and the more I see about it, I'm very enthusiastic, and I feel like I'm making slow progress. But this is just me, working, doing a lot of other things in life, working part-time on this, and not the smartest guy around. And it's, and anyway, I think I'm getting somewhere, but this is very different than kind of 40 years of the smartest people in the world and by the thousands working on something and it not working. It's a different situation.
Let's do another defense of string theory. In an article titled On the Essence of Discovery, Matthew Klebin, once again, he said that what precisely is the definition of theories of physics, and why must all of them live or die by experiment? Since long before the 17th century, and even more so today, mathematicians have unabashedly pursued abstract ideas with no connection to experiment whatsoever. Cosmology was almost entirely unmoved from experiment until the 20th century, when advances in telescope technology made the relevant observations possible. He also cites the study of percolation that found real-world applications much later. And he ends with, the essence of discovery is that you do not know what you will find until you look. Brian Greene also said something similar in an interview where he said, maybe we don't have the technology to work with the energy levels that string theory predicts at the moment. That doesn't mean that we shouldn't work at the moment, because at some point technology will catch up, like telescopes caught up with cosmology. And at that point, it will all make sense. What is your take on these?
Well, I think Yeah, so I mean, one of the main misunderstandings of the argument I was making in my book, and I would make, is that I'm not, I mean, there is a strong argument against string theory that, look, nobody's tested it. You haven't been able to predict anything that you could go out and measure, and nobody's actually done any measurement that agrees with it. So this is a problem. So that's, but as maybe it's clear from explaining kind of my views about mathematics and physics, that I'm actually, ultimately you want to have theories that you can test and you want to be able to assure that you're right. But I'm actually someone who, that's not the primary thing for me. The primary thing is actually, do you have a really compelling new idea and really something that gives new insight and at kind of the deepest structural level of this theory. And I agree fine with Brian or with others who say, well, you should pursue such things even if they're not testable. And I agree. And that's fine. So my argument against string theory, my primary argument has never been that it's not testable. It has always been that it just doesn't explain anything. And it doesn't actually, there is no kind of consistent set of equations you can write down that is compelling and that actually explains something. And so, so it's a bit of a red herring. I'm actually on the same page as a lot of people and agree with them perfectly that yes, as theorists, we should be pursuing things which aren't experimentally testable, by other reasons. And I'm also I spend all my time in mathematics departments among mathematicians. I mean, nothing anyone does in the math department is experimentally testable, none of it, all day. So I see every day that, there's this, you can make huge progress, you can get these new ideas, you can really get somewhere, and by pursuing things away, which has nothing whatsoever to do with going out and looking at the real, and testing it in the real world. So yeah.
I have to ask you a couple of questions about this movement and how it started and how it was sustained. Michael Shermer, the science historian, he once mentioned that Stephen Wolfram had approached him. Wolfram is working on his own theory of everything. He calls it a new kind of science and some powerful ideas about cellular automata and computation. And what Wolfram wanted to know was, how do you start a scientific movement? And Shermer's response was, most of the time, they're never top down. They're always bottom up. So you have to get grad students, researchers, professors so passionate about the idea. It has to be so seductive, so attractive that they start espousing it. Why did string theory become so popular that it launched 2 superstring revolutions as well, despite making no predictions, despite the lack of falsifiability? If this was going to be a case study that'll be studied in the future, as a movement on a psychological level, why did it become so popular?
Well, I think there are 2 things. I mean, one is that, the fundamental problem the whole field has had since 1973 is that the standard model is too good. It's just that, literally every experiment anyone can do looks exactly like this. And so this is a very unusual situation that normally physics has been, there have been these weird experimental results which nobody can explain. And so everybody, and partly because of this, I think physics always had this kind of sociology of, it's very different than math. In math, there's kind of an idea that people should kind of spread out and you should become expert on something and everybody should kind of do their own thing. And in physics, it's much more had always a sociology of that, this new accelerator was built, they turned it on, it found these totally unexpected things. What's that about? How do we explain this? And what does this mean? Yeah. And everybody works on the same thing. So, and everybody jumps in on it and starts working on it. And so the problem was that then you removed, in 1970, you then kind of removed that experimental impetus. Since 1973, there literally has not been an experimental result of that kind at all. So, and the things which seem to be experimental results of that kind actually turn out to be wrong experiments. So but there's still the sociology that you should jump on the new thing and the new idea, and everybody should try and figure out this one thing together. And that's so. When string theory came along, it had been like 10 years of this increasingly frustrating situation of not having no new progress into standard model. Nobody knew how to do better. There was no experimental clues. And then, so then this idea came along, and and it was like, okay, well, this is something new that nobody's really tried before. And also it's very complicated. String theories are very complicated. What you can do with 6 dimensions is very complicated. So there's a huge amount of work to be done. So there's, hundreds of obvious research projects of let's calculate what this 6-dimensional thing does. Let's find some other 6-dimensional things. And you had the great genius of the field telling everybody, this is it, guys, this is it. And so it really was, over the space of a few years from 1980s into the late 80s, it really, anyway, it was kind of a feeding frenzy that everybody was changing what they were doing to try to do this.
Yeah, I apologize for the interruption, but we keep bringing up Ed Witten and the genius of him. Why do you think he believes in string theory so passionately? If he is such a brilliant mind, then why is he not able to spot out the glaring problems with string theory?
Well, I think you fall in love with ideas. It's kind of I think the best explanation is it's like, why does somebody love a certain other person? I don't know. People fall in love with things, and you can fall in love with ideas and their possibilities. And he and some other people fell in love with this idea in 1984. And anyway, I'm not sure what else. What else? And
is this a challenge? Sorry, is this a challenge most researchers face? Like you saw, Einstein was so married to his idea that he couldn't figure out how to handle the cosmological constant, right? Which ended up becoming one of his blunders. Do you have this fear for yourself as well, that you get so married or so well in love with an idea that you, in a way, get blinkered and you don't expand your horizons in a way?
Yeah, but I've certainly had throughout my career, I've come up, there are various ideas I got interested in, and I was very, this is great, this is wonderful. But the reason I'm actually very excited about the Twistors is this is the first time that this is, normally what happens is you do this and then you work on it for a few months or a year or two, and then you start, and as you work on it, you find out more and more things wrong with it. You find out more and more this doesn't work. Or if you like this, whatever, your love interest, you start to realize, find more and more of their flaws, and this doesn't
the imperfections.
And so, yeah, and then sooner or later you say, okay, well, that really wasn't such a great idea, so I better try something else. And that just, anyway. So the question is more kind of why that hasn't happened, but with string theory, but with Witten, I think that there is a very interesting analogy to Einstein, actually. So Einstein also, after general relativity, he never really accepted quantum mechanics and quantum field theory, and what these really, really powerful ideas about quantum theory and geometry, which ended up creating the standard model, were things which he never was interested in. He didn't really want anything to do with that. He had a different idea, and his idea. He had this idea that I'm just going to, I use geometry in a certain way to get general relativity. There are more things to be done with geometry. I can look at more exotic geometries. I can put in extra dimensions. I can and those doing that and doing that is going to give me a unified theory, a theory of everything. So that's what he was doing. And so he actually spent the last 20 years of his life or so at the Institute, working in love with this idea of generalized geometries are going to give me this theory of everything. And Witten's office is kind of just down the hall from where Einstein was doing this. And so it's not, it's not, there is a precedent.
Yeah. In your book, there's a chapter titled The Only Game in Town, where you talk about this problem in academia. You describe this self-sustaining bubble that's being created around string theory and physics in general, which is now so toxic that if there's a grad student who wants to get a PhD or a research position, or a postdoc who's looking for a tenure track academic job, professors looking to publish the papers, or looking for grant money for their summer salary, all of them have to play by the rules that have been set by the string theory community. Some have gone as far as calling it the string theory mafia that controls the community, which plays on this problem in academia, which has been developing over the years, which Eric Weinstein has coined as the embedded growth obligation. Can you expand on this issue in academia today? If I was a grad student starting out today, why would it be tough for me to step away from string theory and explore my own thing and not play by their rules?
Yeah, well, it's more complicated than that, and it's become even more so, since I wrote the book. I mean, this book was written over 20 years ago. Yeah. What's going on now is actually kind of strange. Is that you actually, if you remain a true believer in string theory and say, I'm going to just keep doing exactly this because I believe this, despite what Peter Woit says that it doesn't work. The problem is most other people in the field have actually realized this isn't working. That this vision that seduced Witten and others in '84 has not panned out. You're not going to get a job doing that. You're going to have a lot of trouble getting a job doing that. So actually, there are actually a lot of students who kind of, as they're going along, they read Brian Greene's books. They get very seduced by this and start to believe this, and then they start working on it. And they these days they find they can't get a job either. You're not going to get a job doing. I mean, maybe you can do it. It's very, very hard to get a job that way. So, but the underlying problem that I think drove all this is still the same, which is that this is a subject that's very appealing, very seductive. A lot of very smart people go into it. So, in very rough numbers, I was looking at these numbers when I wrote the book. In very rough numbers, you're talking about maybe 100. Let's just stick to the U.S. Maybe 50, 100 people getting PhDs in this subject in this kind of fundamental theoretical physics, whether it's string theory or other things, and each year. And then if you look, how many permanent positions are there, new permanent positions are there doing this each year. And now you're talking about 5 to 10. So there's kind of a factor of 10 between the people getting PhDs and actually permanent jobs for them. So this creates a dynamic that, if you get a PhD, even if you get a PhD from Harvard or Princeton in the subject, and you want one of those 5 permanent jobs, you really have to do everything right. One possibility is you can go out on your own and make a brilliant Einstein level advance and change the field to get a job. You could do that, but if you're not Einstein and you're operating in a normal way, it's not so hard to get a postdoc, but in a few years I'm going to need a permanent job. What am I going to do? And the committees that are choosing the people for these permanent jobs, what they're doing is they're looking at, several hundred applications from very, very smart people, all of whom have written a bunch of papers and done this stuff, and all of whom have good letters. And typically what they then focus on is, okay, well, amongst all these people, which of them are kind of working on a hot topic, on what is most promising and what everybody seems to think is the way forward. So there's the structure of the whole thing drives people everybody back into this problem the field already has of everybody working on the same thing. So there become some small number of, there's lots of new ideas around, but some small number of them kind of become the ones that are identified. Oh, this is the hot new idea this year. And if you want a permanent job in the field, you better be working on one of those. And if you decide, well, those don't seem to be so great to me, I want to go do something else, you're just not going to get a job. This is just not going to work out for you. So that's this is totally independent of string theory. And what you see now is you see these things. I mean, I can give you a list if you want here are the 3 or 4 hot topics of the last year or two, which you have to be working on if you want a job this year. And, there are things, they're not string theory. Several of them are things which, people like Bryant or Matt Klebin or whatever would tell you that are interesting things that came out of string theory. But there's a very, very, you have a very, very narrow place for, you're forced to work on a very, very narrow range of topics, which, if you want a permanent job in this field, and it's very, that's actually what's kind of the underlying source of the problem, I think.
So how do you break out of this self-fulfilling prophecy? Because you brought up Einstein. I think it's now impossible to do what he did, where you can work at a patent office and also work on theoretical physics. It's become so complicated. You need so much funding. There's so much mental, physical currency that you need now to do research that you can't just probably come up with this breakthrough invention on your own. Like, you have to go through these tracks. But if these tracks now offer such a narrow path, how do you actually break this vicious cycle and get out of it?
I don't know. I think the fact is that we really haven't, and this is one reason why the subject is really not very healthy. It's very hard. You're right. I think part of the problem is that this underlying problem is that the theory that the thing you're trying to do is extremely hard, because the theories that we have are too good, and you don't have experimental clues telling you how to improve them. So you're facing a much harder problem even than Einstein was facing, and it's true that just kind of going off and thinking about yourself about things is not the most promising way to, if you want to get new ideas and make progress on a difficult problem like this, at least to me, I mean, I think what's actually important is to be surrounded by other really smart, knowledgeable people who are doing similar things, right? Who are doing similar things, and then you can get some inspiration and learn new things and learn something new and get a new idea from them. Just working by yourself is very, very hard. So I think that really is the problem. I think people often, saying, "Oh, well, we should just kind of find," and it isn't so much money. And none of this is actually really that expensive. But it is more, providing positions of people in an intellectually rich environment, where they have enough money to live on and enough time to think about these kinds of things. And it's not huge amounts of money, but for whatever reason, there are not that many jobs around like this. And a lot of the problem is just the competitive nature of the field. It's just the fact that we produce 10 times more, 5 to 10 times more PhDs than their jobs for is really a problem. But unfortunately, I don't think the solution is for some rich person to kind of fund people to go off and work by themselves and on exotic ideas, and that it's going to work. It's a little, just thinking about it recently, it's a little bit like somebody is saying, well, these people in this huge plasma physics lab or something haven't been able to create a fusion reactor, so we should, we should. But so the solution to this is to give money to a bunch of people and tell them to go and work in their garages and design a fusion reactor. Well, no, that's not going to work either. So I think you have to change I've always felt that you need to change what's going on at our great research institutions, and yet you have to start by getting people to admit that, if you won't admit that something is wrong, you really can't move forward. And what's been, I just find endlessly frustrating is looking at what's going on at some of the top places in the world, and just seeing people's continuing refusal to even admit, that things haven't worked and that this is staring them in their face. And some of this is due to, the fact that you'd have to admit that the love of your life is really highly problematic. Some of it is, it would create kind of the fact that you've devoted so much of your life to this, and people have been giving you all this money to do this and it hasn't worked, is just not something you want to admit if you want people to give you more money. And there are a lot of reasons why people are not admitting this, but it's very frustrating.
I cannot tell you how shocking it was for me when I actually discovered this bubble of sorts in academia, because science is viewed as the bastion of empiricism, falsifiability. Like in science, you believe that people embrace all ideas and they will reject the ideas that can't be proven. And they often contrast science with religion, for that matter.
Yeah.
But to notice that there's some form of mythology generating within science itself, and there's pocket being created, was shocking for me to discover, because I viewed science as the ultimate.
Yeah, no, it's shocking.
It is shocking. Yeah. Well, it's very interesting what you pointed out. And I hope it changes. Maybe there's someone who comes in who plays by the rules, and while they're in the system, ends up changing it. Fingers crossed. That's all I can hope for. Before we move into our final closing questions, I would love it if you can interpret what I've built with the Lego. What do you think these masterpieces are?
Oh boy, I have no idea. Well, these are definitely eyes here. These are eyes here, but so this is some kind of a face. No, at least it certainly seems to be. But a face of what or who, I have no idea. And this thing. Oh, this is much more difficult. I don't know. That might be a head on something, but I don't know.
Some twisted version of reality. No symmetry in this, but there's definitely a creator. So that the devil's in the details. Okay, let's go into some of our closing questions. What are some books, movies, role models that have strongly influenced you in your life?
I was trying to remember. I mean, a lot of the problem with books or things were role models. I then later on in life kind of decided this maybe there was something this was kind of problematic. So actually, I remember one of my experiences. I remember when I was a teenager was and learning about quantum mechanics was I was reading about the whole story of the history of quantum mechanics, and about some things written by people involved in this. And one is Werner Heisenberg wrote some. There's some wonderful essays and some books about about this birth of quantum mechanics and about his experience and about how this changed the view of the world.
Across the Frontiers.
Across the Frontier, yeah, exactly. That's exactly what I was thinking of, and that and I was very, very struck by that, and just this. Anyway, so I think I can very definitely recommend that. I mean, in later years, though, I mean, you realize some of his stories are about, I was with my friends and, we're discussing these great ideas of philosophy and about, the way the world works and philosophy. And we're going on these hikes in the mountains around Munich or whatever. And then only later in life, you start to realize, wait, young blonde Aryan men going for hikes in the mountains of the 1920s, and you start to realize that this is part of a German tradition which did not end well at all.
Yeah.
So there's that about that, but still, it's a great book. Yeah, Beyond the Frontier, Across the Frontiers. Yeah, and there's that. So that's. I'm trying to think what else has been. I can't think of anything recently that. But that book was certainly very influential, and pretty much anything. Maybe I can recommend that to anybody who doesn't know this whole kind of story of modern physics, from Einstein's developing special relativity and general relativity, and the way quantum mechanics developed during the 1920s. It's one of the great kind of romantic stories of humanity about how all these things were figured out, and it's anyway. It's just fascinating. And reading about it there are a lot of great books about it, but also reading about it by some of the people who are there, like Heisenberg, certainly worthwhile.
If you were granted one wish and you could get the answer to one of the biggest mysteries in the universe, what is the question that you would like to get the answer to?
Oh boy. Well, I guess one of the the main question is what I think about. In much of the time is what is the is there how is there some better more unified theory than the standard model, possibly including gravity, and what does it work, and what is that mathematical structure that's going to make that work? So that's the.
Yeah, we're all looking for that answer. People have spent entire careers looking for that answer. Okay, important question. What would you like your legacy to be?
Oh, I mean, I don't know. I'm actually pretty. I'm actually getting old enough to start worrying about such things. That is, I'm actually 66 now, and I'm actually starting to figure out. Okay, well. I have this weird position at Columbia, and I should need to retire from it at some point. What should I do with my life? But it's I'm actually quite proud of these 2 books that I've written. Of the I'm Not Even Wrong. I think looking back at it, it stands up. It was written quite a while ago, but it stands up very, very well, and especially compared to other things that people were writing around the same time. And I stand behind just about everything in there. I think I'm very proud of that. I also wrote this kind of textbook about quantum mechanics and representation theory, which I think, as years go on, the more I learn, and when I teach the material again, I find more problems with what I wrote there. But I think that was actually a different kind of book than what had been done before, and I'm actually quite proud of that. And then very recently, the last 2 or 3 years, I really have become very, very enthusiastic about these new ideas about twistors and about this. And so I really think there are some new ideas there, which I've been, I've written something about them. I'm still working on them, but anyway. Again, this may be a mistaken love affair, but I'm actually more and more convinced that these are things which are going to be important in the long term.
I think so too. What advice do you have for young people?
I don't know. It's hard. I very often talk to young people who are, undergraduates or graduate students. They want to, how do I have a career? And first of all, how do I have a career? How do I have a career in theoretical physics and do these things? And one thing I have to tell them is, well, my career path was really odd, and I can't recommend that one. That's not going to work probably again. But I got very lucky in many ways. But unfortunately, I think I have to tell more and more. I have to tell the students that you can't. The situation in theoretical physics is just pretty grim, and this job situation you're putting yourself in really is really quite bad. So if you have any interest in both mathematics and physics, I tend to tell students you really should probably go get a PhD in mathematics, and that you're not going to mathematicians aren't it's not part of a standard mathematics research program to work directly on these problems. But there's huge amounts of interesting stuff going on in math, which a lot of which has different connections to physics. And so, you can probably find something really interesting to work on that has some connection to physics. Maybe it'll even someday lead to some advances in physics, and you actually can have a real career and have in a healthy field and maybe get a job. So that's
great advice.
If you have your choice between trying to if you're interested in the same thing as I am, and you have your choice between trying to get a math and a physics PhD, get a math PhD.
That's good advice. So people interested in physics, go to maths. Okay, final question. What do you think is the meaning of life? What is the purpose of all of this, Peter Woit?
I really don't know. My reaction to this question, whenever people ask it, is, I understand why people are, people see these fundamental ideas about physics, that these are, everybody's interested in these kind of deep questions about what is this physical universe that we're part of, and what these and you as a physicist know about it, so you must know something really deep. But I don't know. I guess I see that as very kind of disconnected from the question of the meaning of life and what and humanity and what human beings should really be doing with their time, or how you should see your relation to what's going on around you. So my reaction to this question is often that you're really asking the wrong person. This is somebody who's been sitting around thinking about math and these ideas in physics is really not somebody who has anything particularly helpful probably to tell you about the meaning of life or about this kind of question. So
on a personal level, were you able to derive a meaning for your life or a purpose for yourself through math?
No, it's not. I think, and it's actually kind of maybe one of the difficult things about a career in this kind of mathematics is that it really is that there really is this very unusual complete disjunction between your work, the kind of thing you're working on, and then having a healthy and fulfilling and worthwhile everyday existence, what you do every day, and how you interact with the people around you. They're really two different things, and and really devoting yourself and really getting good at and really getting deeply involved in these questions about mathematics and physics is actually not really very healthy for being a normal human being and being nice and treating the people around you well and having a normal, decent life. They're really not. Yeah. So being good at anyway. So you end up kind of having to manage this disjunction between these two different things in life.
Professor, thank you so much. If people want to connect with you, read your book, read your blog, where can they do so?
Oh yeah. So the blog, I said, is easy to find. It's not even wrong. And also I try to get to maintain a fairly complete list of all the things that I've written and talks that I've given and course materials from courses that I'm teaching on my website at the Columbia Math Department. So if you find my website, you'll find a fairly complete list of all the things, things I've been doing or that whatever I've been attempting to try to make available to people.
I definitely recommend it, and definitely recommend if people want to dive deep into Twistor Theory, they can read Space-Time is Right-Handed, the latest paper. Professor, thank you so much. It was an honor talking to you.
Okay, thank you.